So here's what we started looking at. We were reviewing plotting motion. And as we reviewed plotting motion, what we did here is that we looked at constant velocity. And another thing that we looked at was changing velocity. So what I'd like to do here is that I want to go back and focus on those particular things here. So the slope tells us two things. It tells us about the magnitude of the slope, and it tells us the direction of the slope. So when I look at the magnitude of the slope, the higher the slope, the larger the slope, the faster the object is moving. The lower the slope or the smaller the slope, the slower the car is moving. And then we look at the sign of the slope. That is, if I have a positive slope, then it's moving to the right, which is what we typically define as the positive direction. On the other hand, if we're moving in the negative direction, that is, then I have a negative slope, then I'm moving to the left or the negative direction. So plots can be non-intuitive. So the way we make plots intuitive is that we connect motion diagrams to these motion plots. And it will make it easier for us to comprehend what is going on. So this was one of the examples that we did before. So I separated out a motion plot versus motion diagrams. And what we're seeing here is that I have two lines. I have a red line and I have a green line. One of the things that I see about the red line is that it's not as steep of a slope, but it's in the positive direction that it's sloping. On the other hand, the green line has a very steep slope, but at the same time, it's in the negative slope direction. So if I now connect that with the motion diagram, I look at my red line, I see that I have a smaller slope, so it has to be moving slower. The fact that it has a positive slope, that means it must be moving to the right. So if I look at my motion diagram, you could see that I define my origin right here. And so if I look at my graph, you could see that 0 is the origin. 0.1 is closer to the origin than 0.3. So therefore, when I look at 0.1, it has to be closer to the origin, and it's going to the right in the positive direction. So you could see that I have a smaller constant velocity as I go from 0.1 to 0.2, as this graph shows. So that red line and this motion diagram are one and the same thing. Now I look at the green line. As I look at the green line, okay, somebody needs to mute that, please. So when I look at that green line, you see here is that there's a larger slope. So therefore, it has to be moving faster. However, the slope is in the downward direction. In other words, a negative slope. So therefore, it has to be moving to the left. Now, earlier, we just said that 1 is closer to the origin than 3. So look how I put my 0.3. It's farther than points 1 and 2, as the graph shows. So now, because it's moving at a constant velocity, you could see that it has a longer length, and it passes through the origin, because you could see that it passes through the the x equal to 0 line, and it continues going to the left here. So when I look at these motion plots, that's exactly what we're looking at. Now, the other thing that we focused on was changing velocity. So in this case, we only focus on the cases where we have a changing speed and a constant direction. In other words, we are only focusing on speeding up and slowing down. As I said before, if we had constant speed and changing direction, it turns out that the algebra is more intense and it's less intuitive. So we'll just wait for that until like chapter 5 or 6 to actually start looking at that. So here we go. Let's talk about speeding up. So when I look at speeding up, what we know here is that you see here is that I've listed 4 points, 0 to 3. I can only define my speed at 0.1 because I need an interval to travel. And you could see as I go from 0 to 1, that's a tiny little displacement. Whereas if I go from 1 to 2, that's a larger, and from point 2 to 3, it's even larger. So the fact that my displacement is larger for equal amounts of time, that means that my speed at point 1, 2, and 3 increase in value. But if I start to look at this in the language of graphs or plots, we could see here that delta x1 over delta t, that rise over the run, that has to be less steep, because that's what we mean by the slope. Whereas if I go from 2 to 3, that's a bigger displacement, so that has to be a steeper slope. So what we're seeing here is that because the car or the object is speeding up, we constantly have increasing slopes. So if I start to look at this thing, what I'm seeing here is that the car starts at rest at point 0. So you can see here is that during this interval, I have 0 slope. So therefore, that car is at rest. Now, as the car changes displacement, you could see that initially that delta x1 is small. And then I get to delta x2, which is larger. In other words, my slopes are getting steeper. And then finally, I'm seeing a bigger slope between points 2 and 3, indicating that I am going faster. Now, this is a segmented line. Nature tells us that things are smooth. So what do I know about the speeds here? So when I have a smooth curve, I initially can then come in and just say, what is the slope at this point? Well, the fact that the slope is 0 tells me that the speed there is 0. Now, as I increase my slope, you could see that the slope here, that tells me here that in this case, this is my speed 2, and this is not 0. But if I now compare that slope to this slope right here, which is even steeper, you can see here that this slope is larger, therefore indicating that the speed is changing because those slopes are changing as well. Now I can do the same thing for slowing down. So if I slow down, again, we look at our intervals. If I look at my intervals, you could see that the interval between 0 and 1 and 0 and 2, 1 and 2 and 2 and 3 and 3 and 4 are getting smaller and smaller and smaller, just like we saw with speeding up. Instead of increasing, they're decreasing. So since the first point, delta x1 over t, delta t is steeper, we know that as we go to delta x3 over delta t, it's less steep. We see that we're seeing constantly decreasing slopes. So again, going off of what we just did here, you could see here is that initially the slope has to be big. In other words, delta x1 has to be large, and then delta x2 gets smaller. Delta x3 even gets smaller, whereas delta x4 goes to 0 because it comes to rest. So now, smoothing out the curve that we did before, I play the same game here. And so what I'm seeing here is that if I look at the slope at this point here, you can see here that I have a steep curve. And as if I move along the curve, you're seeing that the slope is decreasing. In other words, V3 is large and not equal to 0. V2 is slowing down here because the slope is smaller. And then finally, when I get to this point here, at the very peak, let's say, you could see that the slope is 0. So that tells me that the slope is 0 at that point, and therefore its speed is 0. Okay, that ends the review. So now we are on lecture 2.2, where we're now going to look at acceleration, and we're going to start looking at mathematically solving equations here. So acceleration. Let's start with acceleration. So every time one changes velocity, one accelerates. And you're going to see here that acceleration is different than everyday language. Okay. And we defined acceleration mainly by the direction of the acceleration. We don't differentiate between acceleration and deceleration. We call it acceleration the whole time. And you'll see that the language can get a little bit tedious, and I'll try to use everyday language to make sure that we are looking at this. So here we go. So what we say here is that when we look at acceleration, that implies that we change velocity. And as we already said, there are two ways to change velocity. We can change speed while holding constant direction. Or we can have constant speed while we change direction. We are only interested in the first situation. We are not going to do that. And like I said, we'll wait for this a little bit until chapter 5 or 6. So this immediately implies that we're only looking at speeding up and slowing down. That's the only thing that we can handle here. So now what we know here is that acceleration is a vector, which means that it has both magnitude and direction. So what I'm going to do here is that I'm going to split both of those out. So I'm going to start with the magnitude of the acceleration, and then I'll get to the direction of the acceleration. So here I go. So now let's start with the magnitude of acceleration. So before I get started, one of the goals for you is to not mix up velocity and acceleration. It's easy to mix up. Okay? That's a good goal to have. And it's normal to mix it up in the beginning. So you just got to keep working on that to not mix those up. Here, let me bring up the chat so in case somebody asks a question. So here I go. Acceleration is how quickly velocity changes. And the way we write this is we then say that the magnitude of the acceleration, we typically write as A, and this is the rate at which velocity changes. This is the definition of acceleration right here. So now my job is to physically interpret this so that it makes sense when you look at this. Okay, so now here we go. So now to physically interpret this, to physically interpret acceleration, we will use your body's motion. So here's what I mean. So the first thing that you should see here is that while stopping, in a car, what you're going to find here is that your body moves forward. On the other hand, while speeding up, in a car, your body moves backwards. We want to use that to gauge the magnitude or the strength of the acceleration. So in other words, the strength / magnitude of the acceleration is a measure of the strength of your body's motion. So now, this is kind of the way you should be thinking about it. Okay, so I'm using your intuition to actually think about this. Now, here I go. So the first thing that we should look at here is that if you stop slowly. So what do I mean by stop slowly? That means you're stopping over a large time interval. What happens to your body? Your body moves slightly. The word slightly is a slippery one. Forward. I don't want to use the word push, but a lot of people say like, oh, my body's being pushed forward. It's not. But your body moves slightly forward. This slight forward motion means that you have a small acceleration. So if I look at this equation-wise, what I'm seeing here is that I have to look at my velocity change. That's what we're doing. So what I'm doing in this case here is that I am picking a long time interval, right? That's what I mean this here. This is a long time interval. And as a consequence, I have a small acceleration. Now, on the other hand, if you stop quickly now, what do I mean by quickly? That means that quickly means that you have a short time interval. Then what you're finding here is that your body moves, for lack of a better word, strongly forward. It's like you're being thrown forward, but you're not being thrown forward. That's a misconception. Okay, that's a misconception. So as a consequence, you now have a large acceleration. So that means even though my change in velocity has not changed, what happened was is that I did it over a short time. And as a consequence, I had a large acceleration. So physically, that's how we measure acceleration with our body. But now let's draw pictures to get a sense of this. So now, picture-wise, what does this look like? Well, let's imagine that we have two cars, okay? So what I'm going to do here is that I'm going to say that I have these two cars, and I'm going to... And so what I'm going to have here is that I'm going to have this car, and in this case here, we're going to have that this is my red car. And what I know here is that this car is moving in this direction right there. And for the sake of argument, we're going to say that this car is moving 35 miles an hour. Now, what is this car going to do? Well, this car sees up ahead a stop sign. Right? So here is my stop sign right there. And so what we know here is that in this situation, we know that the car has to come to rest right there. Now, I have a green car as well. And this car is also traveling 35 miles an hour. And once again, this car also has a stop sign all the way over here. And so the goal here is, of course, to stop at the stop sign because you're an upstanding citizen here. So here's what we're doing here. So what we know here is that the brake time for the red car following, up here, that if you stop slowly, that means you have a long braking distance, right? You are now applying the braking distance. And so you have a long time to come to rest. So what actually happens? Well, we're going to say here that this gives me a long braking time. Maybe I should say that this is delta t, and that implies that this is a long braking time. So what does your body do? Your body's motion, let's say, moves in this direction, and we're going to say that this is the direction of your body's motion. You're moving in the forward direction as you're slowing down. You just feel that slow nudge here. So in this case, what we say here is that let's look at both of the cars. Both of the cars are going to want to stop at the stop sign. So in each of these situations, my change in velocity in both of these is exactly the same. I'm going from 35 miles an hour to 0. But this guy is happening over a large time interval. So therefore, I have a small acceleration. And I feel the small acceleration because my body's motion is just slightly. Now let's go back to the green car. So when I look at the green car, unknown to you, as you're driving, a little kid runs out in front of you, right? So this little kid right here is standing in the street, and hopefully you don't speed up because you see the little kid. You try to stop as quickly as possible. So in other words, your braking distance now is much shorter. So the green car has a braking distance, and again, look at the speed change. I still have to stop within this thing. So what happens if you suddenly stop very, 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 very quickly? What happens here is that you feel a very strong motion that your body is now moving in this direction. So now when you look at your body's direction, it is large. You are moving very strongly in the forward direction. You know what we forgot to do here? We forgot to put the driver of the car, right? We need people to drive cars. So now what we're seeing here is that this time interval is a short braking time. So now when I look at this acceleration, we're seeing that this guy is small, and something small in the denominator gives me a large acceleration. So you can judge the magnitude of the acceleration, right? So the magnitude of the acceleration is indicated by the forward motion of your body. In other words, if you slightly move forward, that means that you have a small magnitude of acceleration. If you strongly move forward, then that means you have a large magnitude of acceleration. So you inherently know how you speed up and slow down. I mean, excuse me, how the magnitude of the acceleration is. So now let's move to the next thing. So we just finished talking about the magnitude acceleration to give you a feel for what's actually happening. Now let's talk about the direction of acceleration. Once again, we use your body to determine the direction of the acceleration. And here's what we know. The acceleration direction is always opposite to your body's motion. So let's look at this thing. Remember, we're only talking about speeding up and slowing down. So what do we find here? If you are slowing down / stopping, what do we know? Well, we have our car, And when we're looking at our car here, what we're seeing here is that you feel intrinsic forces in your body as you slow down. So in other words, as my velocity is moving in this direction, what you're finding here is that as I brake, right? As I brake here, I'm finding here that my body is doing what? This is the direction of my body. As a consequence, we then say that the acceleration is then in the opposite direction of the body's motion. In other words, if I was to combine these, I would say this. If I have my velocity in this direction, then if I have an acceleration in the opposite direction, this here tells me that I am slowing down. And this right here represents the motion diagram for slowing down that includes acceleration now. On the other hand, if I'm speeding up, what do I see here? Well, if I look at my car again, what does the person feel? So in this case, the car is still moving in the forward direction, just like before. But now, if you speed up, you get a sense that you are being pushed back into the car seat. That means your body's direction is moving in the opposite direction of the velocity. Therefore, the acceleration is in the forward direction. So if I was to put this together, you can see here that the velocity is in this direction, but in this situation, the acceleration is also in the same direction as the velocity. This is what we mean by speeding up. And this is what our motion diagram looks like for this situation. Now, we have to change language here now. Okay, so this is a language thing. And this is how we define acceleration in physics. The language of acceleration in physics is different than everyday language. By definition, the direction of velocity is always positive. It's always positive. So now, what do I mean by that? So if I have a velocity in this direction, that is automatically positive. If I have a velocity in this direction, that is automatically positive. So how we define speeding up and slowing down is only defined by the direction of the acceleration. So what we say here is that now if my acceleration is in the opposite direction, note that that's negative. If my acceleration is in the same direction as the velocity, that is positive. So what do we call this? We call this negative acceleration. And as soon as you say negative acceleration, it tells you that you're slowing down. So we call that acceleration, but in everyday language, what do they call it? They call it deceleration or slowing down. We don't do that in physics. Because the acceleration is in the same direction as the velocity, we call that positive acceleration. And you're going to see that when we start to look at this thing mathematically, it makes more sense. So as a consequence, this means speeding up. So in both situations, we say acceleration. Even if we're slowing down, we say that the car is accelerating. We don't say decelerating. We say that it's negative acceleration. So you got to be careful with the language. So before we move on, I want to look at the units of acceleration to show you what this actually means here. So to try to put this into the picture here, here's what I mean by this. So let's look at the units of acceleration. And what I'm trying to do here is to show the difference between positive versus negative acceleration. So let's look at this here. So what do I know here? So suppose or assume a car has a constant. Another way that we say constant is uniform acceleration. In fact, in this course, we can only assume constant acceleration situations. If we cannot assume constant acceleration, then the problem is beyond the scope of this course. Now, when we get to energy and momentum, we actually can look at different situations. So here we go. So what do I know about acceleration? Well, what we're seeing here is that by definition, the acceleration is the velocity, the change in velocity over the change in time interval. So let's be careful how I write this now. So the first thing that I'm going to say here is that when I look at this guy here, this tells us by how much velocity changes. And that one is that's really, really important. Because almost all the time what you're going to find here is that the time interval is typically the same. So this tells us about the time interval. So the time interval really doesn't have a lot to do with it. It's really the change in velocity that we want to look at. So here we go. So let's look at two examples to show you what I mean. So the first one that I'm going to do is that I'm going to focus on this guy, and I'm going to say that I have an acceleration that is positive acceleration. And the way we look at this, remember, it's the change in velocity over the time interval, and I'm going to say that this changes by 5 meters per second every 1 second. And I'm going to say that this is the proper way to write acceleration. We'll get lazy and we'll write it slightly different in the future, but this is the proper way. And I'll show you something slightly different in a moment here. So here we go. So what does this mean here? So now let's look at its motion diagram. So let's say that we have an object that starts at rest. So right now, I'm going to say that this here is at point 0, this is 0. So now what happens here? This object is speeding up. Why? Because of this positive sign right here. That is telling me that it is speeding up. It has positive acceleration. So what does it do? It changes my velocity. So, and that means here is that after 1 second, okay, so I'm going to say that this is 1 second now. What this is telling me here is that my velocity has changed by 5 meters a second. So if I start at 0, then that means after this amount of time, my car now is now traveling at a speed difference. Now look at the speed difference here, right? So my speed difference here is 5 minus 0, which will then tell me that this is 5 meters per second. That's what that acceleration is telling me. After 2 seconds, now my speed has changed by 5 meters a second every 1 second. So that means here that my speed change now is going to change by 5. So it's got to go from 10. It's got to go from 5 to 10. So therefore, this guy is now longer because it's now moving 10 meters a second. So you could see how it's changing by increments of 5. And then after 3 seconds, this arrow is even longer because my velocity interval has now changed from 10 to 15. So now this object is now moving at 15 meters a second. So it's telling me that if I have a positive acceleration, my velocity keeps changing in the positive direction. On the other hand, if I am slowing down, I then can have an acceleration here that has a negative sign. So if this has a negative sign, like this, then we could say that this car is changing speed every 1 second by negative 10 meters per second. So this immediately tells me, this sign right here tells me that I am slowing down. So then here I go. I start with my dots here now. Let me put it down a little bit further. So I know that at point 0, let's say that this object is now moving at, let's say, 50 meters per second. At some point in the future, let's say that this is 1 second, and I should have been putting 0 seconds here. You could see here is that by having a negative acceleration, it's going to decrease this amount. So that means it's going to decrease my velocity. It starts at 50 here. And what's it going to do here is that it's going to reduce this thing by minus 10, which then gives me a value of 40. So that means this guy right here is now moving at 40 meters a second. And then let's say after 2 seconds, now my change in velocity is changing again by minus 10 meters, but now it was going 40, so now it is moving 30 meters a second. So then my arrow is now smaller because it's looking something like this here. So you're seeing that my accelerations are changing my velocity by the same amount every single time. That's why we call these guys positive and negative velocity.